is Catherine Brooks, and she will talk about reducing drag, improving performance, the study of V-shaped driblets on
Wrong way.
on shipping vessel hulls.
Yes. Good morning. Sorry about that slide issue. Again, I'm Catherine Ryu, and I'm a sophomore at Liberty University studying mechanical engineering. This is what I've been working on for the past 2 semesters with my professor, Professor Werner. So before I get into everything, I just wanted to go over a brief overview to give you guys an idea of what I'll be going over. I want to make sure that there's some room for questions at the end in case you guys have any. So I want to start with some background, why we're doing this, where it came from, some research questions we had going into it, our findings from this research, and then conclusions and points for future research. So what's the motivation here? The HFO, or heavy fuel oil, price crisis. So right here you can see this plot where we have the months here on the bottom, our number of barrels here, and dollars per barrel of USD. And down here on the bottom, this is for 2020, and then this one up here is for 2021. So as you can see, over the course of this 1 year, there's been a drastic increase in fuel, and in fact about 100% or 80% fuel increase, which is insane. And with this increase, there hasn't been a way to help reduce this cost for the shipping industry. So how can we mitigate these price increases? So starting with our motivation, fuel cost reduction, we move into how can we recover some of these costs? So when we look at how a shipping vessel works and where its energy goes to, about 60% of its fuel goes to overcoming just drag. So what if we reduce the drag by just a little bit? That would have a huge impact, right? So we reduce the drag. We were inspired by these shark skin riblets, little teeny tiny itty bitty riblets that help a shark move faster through the water. But in order to maximize the impact of this solution, we want to be able to implement it on the most common shipping vessels. So we did some research looking into what shipping vessels would be the best pick for this. We landed on the handy-sized vessel, where all these numbers over here represent the different tonnages that each vessel can carry. This vessel is typically about 150 meters long, and it's optimal for shipping and is the most commonly used one, simply because it's able to go longer distances and carry large amounts of tonnage while still being able to go into smaller canals and deliver things straight to major cities. So it's a great application for this research, as it will have a very, apologies about that, very broad impact from a little change. So this is what we arrived at, this simplified geometry, not to scale, of these riblets. Which now leads us into our objective for this whole research, which is to simulate the flow over these riblets and identify the effect that it has on drag, and then connect that to drag reduction. How is this going to affect HFO consumption as well? So how do these work? Little bumps over the surface of it. What does it do? So over here we have a representation of this geometry, and these little vortices here representing the water as it flows over the surface, with this arrow representing more water. So as this water is flowing over here, you can see that it's not interacting with the flow going straight over. It's not interacting with the material down in here. So it's only interacting with the top parts of this geometry and the water, which this fluid-on-fluid interaction has a better skin friction coefficient than material on fluid. So research by both Dean and Fu have found that these riblets can have an effect of up to 10% in drag reduction. Now there is a trade-off with these riblets. You have to find ones that are also more durable so that they can withstand flow. So with the one that we selected, it has about a 5% drag reduction rate as tested by other people. So now I want to go into the difference between these riblets and surface roughness. So how can we know that these riblets aren't going to have the same effect as something like barnacles? Because those are bad. We all know barnacles are bad. But the main difference here is that these have a repeating geometry that have this ratio here of height to width. So with this H/S ratio, it's been found that a ratio of about 1 means that there will be drag reduction effects. And if you're having a surface like this that is rough, bumpy, irregular, it's just not going to have that same sort of ratio really anywhere. So there are a lot of other things that went into this riblet selection. There have been a lot of other ideas for riblets and how to manufacture them to be more efficient. This here is an apparatus to test whether or not spacing in between the riblets would have a positive effect on drag reduction. Didn't end up being super helpful. And this right here was a test to see whether or not having a space underneath the riblets and using the pressure difference with the water to see if that would have a positive effect on drag reduction. That didn't end up working at all. But these right here, that ends up being better because these right here are much simpler geometries to manufacture and implement over like a huge surface like the hull of a ship, right? This one right here is the one that has the highest, which is 10%, but as you can see, it's probably not going to hold up super well in water for a long period of time. Same with this one. So while this one does have a lower drag reduction, it is the most durable out of the three. So that's the one that we picked for like a larger surface like a ship. So in the end, this is the scaling of it. We have a length of the entire ship, which in our case would be about 150 meters. And then the draught here, which is about 13 meters, which would be the difference between the surface of the water and the bottom of the hull. And then the previously defined H and S values. So before we went right into simulating flow over this flat plate, or the riblet surface, we wanted to start with a flat plate. This would give us an idea of whether or not our boundary conditions would be sufficient to approximate the flow over these riblets, because we were kind of guessing and approximating here as far as the flow over a ship. So we ended up arriving on a flat plate to estimate that, even with the curvature in the waves, just as a preliminary approximate study. So here we have right here on this differential volume, we have the pink surface here, which would represent the no slip surface, which is right on the surface of the hull, where no velocity would be occurring. And then this blue surface up here, which is free slip surface, which would be where the water comes in contact with the air, and that fluid on fluid interaction has no shear stress. And then here we have the hydrostatic pressure, this one representing the gradient as it increases with depth. And then we have an outlet back here and an outlet right here, along with the velocity inlet, and then gravity coming in through the top as well. So overall, there are 3 outlets, 2 walls, and then 1 inlet for the velocity. Now for the mesh, we need to make sure that it was going to be able to capture what we were looking at so that we could actually see if this approximation was good. So we have, as it approaches the surface, it gets smaller and smaller and smaller. And here's another view with this being the boundary layer right here. We ended up with a velocity of about 13.9 meters per second, which is kind of an average speed for some of these vessels. It varies depending on who you ask. And then the density and viscosity of the salt water. So some of the obstacles that we had to overcome before we could simulate this was whether or not we wanted transient or steady flow. With transient flow, it would probably be better for simulating some of the vortex shedding that would occur further down the plate. But due to the resources that we had, it was not really realistic for us to simulate this transient flow. So we went for steady and did a study to make sure that this would be an appropriate approximation. And for our viscous model, we landed on K epsilon for, again, a simpler model for a preliminary study, with hopes of maybe transitioning to LES or a hybrid model to be able to better capture that boundary layer. So once we took a look at our mesh, we were shooting for an orthogonality quality between 0.2 and 0.4, landed on a quality of 0.2, which was good for our purposes. And then here's a preliminary geometry for the riblet surface. We haven't gotten to a point where we've been able to simulate the flow over it, but we have finalized the geometry. So right here is the free slip surface that's in contact with where the water is in contact with the air again. And then down here, this pink section is the riblets, which would be the surface of the hull, the new surface of the hull. And we have our little scaling here in case you're curious. So the plan would be for this simulation, it's a little complex because of the level of riblets that we have. because just for a 13-meter section of this ship, it's about 1,000 rivets. And that's 2 surfaces on each side, and for a 150-meter long ship, that's a lot of surfaces for ASCE to chug, and it does not like doing that. So we're planning on implementing journal files to use differential chunks of the hull, and then differentially compute along the surface of the hull what those properties would be. So our findings for the flat plate, which you can see over here, we did a convergence study to see how it converges with the expected skin friction coefficient and Reynolds number curve. So this red curve and the dashed curve represent the theoretical, while these other ones are our tested ones. So this y is the distance from the plate, so at different levels of y up here, going from 0.2 to 0.9. And as you can see, at the lower levels of y, we kind of have these squiggles here, these bumps. I'll get into that on the next slide, but the accuracy that we're looking for here with this study is that there's low residuals as well as convergence. So as you can see, there is convergence, but we wanted to make sure that this also was coupled with low residuals to make sure that it wasn't only accurate, but it was correct. So we have low residuals and convergence, which means it was a good approximation for our case. So right here is the answer to the question, why is it that there were little bumps? So here's the y velocity from the distance of that plate. And as you can see, as you get further away from the plate, we're having less velocity in the y direction. So we're thinking that's probably because of the hydrostatic pressure creating more velocity and backwashing it. And then here we also have some funkiness going on the sides where the velocity is cycling back through on this side, the pressure is coming in on this side when it's not supposed to, it's just supposed to be on the surface. So that could be solved pretty easily by just having another volume for the velocity inlet to start at, and instead of having it start all at the same spot. So having like a spot for it to flow over before it enters our differential volume. So what does this mean for future research? In the short term, we want to see if we can apply these verified boundary conditions to a riblet surface, maybe honing in on some more precise boundary conditions, and then compare a cost and benefit analysis, covering the portions of the vessel to see how that has an effect on drag reduction. Because what if we just put a couple riblets here, a couple riblets here, a couple riblets here, instead of covering the entire surface of the hull? We want to see if that has about the same effect, because maybe that would be a better cost or more cost productive than installing it over the entire surface and would have a similar effect on drag. We also want to optimize those boundary conditions. And for a long term, a couple ideas, we were wanting to explore the selected geometry and see if it has some positive effects on anti-fouling. There has been some research into using similar microstructures to actually prevent anti-fouling. So those two things together could have a 2-for-1 deal, be able to prevent drag in the current and also prevent it from occurring later. And then also see if we can implement a similar structure to the shark skin where they have like variation in riblets. Because as you continue down the shark, they might have smaller riblets up front, maybe some wider riblets here. They'll have variation as it continues down their body. Curious to see maybe if we had some smaller riblets in the front, larger riblets in the middle, smaller riblets in the back, what effect would that have? And then also incorporate some hull curvature and waves to see how that affects the simulation as well. So overall conclusions. In a hypothetical situation, if this was implemented in a typical handy-sized vessel, they consume between 20 to 25 tons of HFO per day, with about 12 to 15 of those tons going to drag reduction, or overcoming drag, as previously said, with that 60% chunk, so a lot of it. If that was reduced by just 5% in a very broad hypothetical scenario on the lower end, it has the possibility of reducing costs by $150,000 a year and saving 3,000 tons of HFO per year, assuming that these vessels are running on a semi-daily basis. And even more huge is the impact on the amount of these vessels that are making transatlantic trips, how much that could save. So overall, the simplified imitation riblets have a positive effect on drag reduction and have the ability to reduce fuel costs. And then the boundary conditions that we did work on are a good approximation for ANSYS Fluent and would be applicable in a riblet situation. So here are some of our references. And are there any questions?
Very nice. Questions for the speaker?
Yes, very impressive presentation, especially for sophomore. Do you think they are different if it is not applied to a vessel but an aircraft?
That's a great question, yeah. So it does actually change in an air environment because the properties of air would be a little different. But if you see something like on a golf ball, how they have dimples on them, that has been looked into to apply to an aircraft as well, a sort of dimple design. I actually live near a flight test base, and I went to a museum, and they actually put a nose on a plane with dimples in it, like a golf ball, just to see what would happen. And so there has been some looking into that to see what that would do. But that could have a really good effect on air travel as well. So, routing impacts.
How
Yes,
do
sir.
you determine the size of the ribbons,
Great question, yeah.
like the angles and the
Yes, sir.
size of it?
So we were looking at some previous studies done, and two researchers, Dean and Fu, had looked into a lot implementing with that specific structure and shape, and they landed on like a width of 0.2322 and a height of 0.13 was their optimum ratio. So we went with that because that was already determined to be a good ratio.
Do you actually do an optimization in that work?
The
one you
researchers,
referenced?
yes, they did. They had like a whole plot showing with the different lengths, and I didn't put that on here. I apologize for that, but
No, that's fine. Okay.
there was a study on that. Yeah, good question. Yes, ma'am.
Could you tell me what is the difference between the numerical simulation and the experimental results? What you showed this after distance, you have the blue, I guess, yes, blue curve and brown triangles. Yes.
Yes, yeah. So the distance would be the y distance. So over here you have the y-axis up here going up.
Mm-hmm.
So that would just be
But
the
these
distance.
are measured, yes?
Oh, I believe that's in millimeters.
Simulation.
These are also simulations?
Yeah.
Oh, I'm sorry.
Sorry.
I apologize.
I saw that these are experimental
Yeah,
results.
no, the red curve is experimental.
Oh,
black
yes,
curve is
yes.
experimental.
Sorry, I misunderstood your question.
Okay.
Any other questions?
Well, great presentation. I just want to thank you for your presentation. So you mentioned that the optimal ratio for the riblets, it's 1.
Mhm.
You said something like that. So I was thinking like the height of the riblet, what for this simulation I did, what exactly was the height you consider? So must that be the case in all the cases? It has to be 1? Because there might be some situation where maybe you just want to be flexible about the height.
Yeah.
Did you consider that, or it just have to be 1? The ratio has to be 1 for you to get the results you have told us about it.
Yeah. So I must have misspoke there. I meant around 1 was the idea.
It's around 1.
approximately 1.
Okay.
So it is around 1. But if
So
it's like, you know, greater, I think it was like less than or about equal to 1. was
Okay,
the-
so there's a bit of tolerance for
Mhm.
that. Okay, that
Yeah.
makes sense.
Yeah.
Thank
And with
you.
the barnacles and stuff, that's not really something you see.
Yeah, okay.
Yeah, good question.
I have one more question. I think based to my understanding, for now your riblets are perfectly rigid, right?
Yes, sir.
Do you plan to extend that to some flexible riblets? Because I guess in real life, on the sharks, these are flexible. Do you think that would play a role?
Yeah, that's a really good consideration too. I think the trade-off would be whether or not they would be durable enough to withstand like longer periods of use. Because that flexibility does come into play. But another thing that actually helps them too is having the surface heated. because their skin is heating it. So if we had a heated hull, that could also have a similar positive effect, because there are lots of layers to what contributes to that drag reduction, which is why at the moment it's only like 5 to 10%, which is pretty big, but in the grand scheme of things, it could be bigger if things like that were implemented. So it would be a trade-off.
Nice.
I like that your question. I was just trying to make a suggestion. It's not a question. Like,
Yes, sir.
maybe you could add to your list of future research, like the riblets at different angles of inclination.
Oh, that's a good idea too.
Yeah, so
Yes,
you
sir.
will be able to see exactly the answer to the question that he asked. Like, the riblet is at angle 30, angle 20, angle 15.
Yes, sir.
What is the effect of that on the drag? I think that's what you're trying to get, right? Yeah, kind of.
Well, also, if they're perfectly rigid or flexible, that
That will
they
be
change
fun,
orientation
right?
as
Like when the
the
real
flow.
shark
Yeah.
is moving,
Right.
like,
Yeah.
you know, it's natural. It's got that
Right,
design,
sure,
so
yeah,
it
yeah,
kind
yeah.
of like move like that. So when we have different angles
Mhm.
and we have the plot for
Mhm.
that can inform us to
Sure,
know,
yeah.
to make that dynamic.
Right.
Yeah, that's a good idea too.
Great, okay, let's thank our speaker again.